going to do is we're going to introduce one-dimensional motion. So as we start looking at things, we've got to make sure we have some very good definitions. And we have to start considering the motion of particles. So what we're doing in kinematics is we're looking at the particles and we're looking at their motion without regard to what's causing the motion. So we're going to get to forces later on, but with kinematics, we can do an awful lot of looking at those equations of motion. So we're going to treat things as particles for right now, and we're going to start kind of looking at some definitions. So we're going to make sure that we've got those initial definitions. So we said that physics is the study of related to matter. That's the stuff of the universe. That we look at the energy, we're looking at motion, and we're looking at force. So as we start moving through our book, and I've done these slides for a variety of different books, but our first chapter was on unit analysis and estimations and getting some framework to give us a guidance as to what makes total sense. So now we're going to look at motion, and we're going to look at how that's going. So one of the things we have to talk about is displacement. So when we think of how something moves along a number line, we're looking at where we start and where we finish. And some of you have already taken chemistry, some of you have taken a few other things, and you might have heard the idea of a state function. And that state function says that it only matters where we start and where we finish. But when we think about motion, like a trip down the road, we're thinking about how far did we travel. And we can look at that two different ways. So let's say I start out at my house and I'm coming to campus and I forgot something and I go back to my house. And so I have traveled twice the distance from my house to my campus, but my displacement is where I started and where I finished. I'm still back at the house. So I didn't actually move. So I didn't have that displacement. And we're going to use that terminology. So distance traveled and displacement might be the same thing, but it might not be the same thing. So we're looking at how things go. So when we're dealing with motion, we're going to deal with three concepts. And we're starting with engineering physics. So we're starting with that first concept of how we're going to look at it. And so there's going to be a couple of caveats as we move through. In this course, we're going to take acceleration as a constant. Now we can have variable acceleration, for example. So let's say I'm at the stop sign and I'm deciding to move my car. I can put my foot on the accelerator pedal, right? We're going to go from 0 to some speed, or we're going to go to 0 to some velocity. And we're going to talk about that here in a second. But I can do that with a steady pressure on the car and I'm traveling at a constant acceleration, or I can do the, where I'm doing a variable acceleration. For the purpose of simplicity and introducing the concepts, we're going to stay with that constant acceleration. So we're looking at displacement. Where did I start and where did I finish? We're going to look at velocity. Now, velocity is very special. Velocity and acceleration both, and displacement, they're all vector quantities. So when you're thinking about those terminologies about vectors, all right, and in mathematics, a vector is going to have a direction and magnitude. It's going to have a size and it's going to have a direction. And if you remember back in your math classes, we can talk about unit vectors. And a unit vector has a magnitude of 1. Okay, it's got a magnitude of 1 and it's going to help us tell the direction. And we typically use the letters I, the letters J, and the letter K for that direction. So we're going to get that direction, I, J, and K, or X, Y, and Z. And we're going to look at that particular part. So, but displacement looks at where I start and where I finish. Velocity is going to be how fast we're going, and how fast is going to have a different kind of meaning for us here. And so we're going to look at that particular part of it. But velocity is going to have a direction. I'm traveling north, south, east, and west. The wind's coming out of the northwest. The wind has a northwesterly vector to it. Those are things that we've talked about in the past, or have been talked about in the past, and you're probably familiar with. Acceleration also is a vector, and we're going to deal with that. So we're going to talk about our full frame of reference. So when we're dealing with one dimension, we usually use X, right? When we're dealing with an up and down, we usually use Y. And if we're in 3 dimensions, we can have an X, Y, and Z. But we are going to use for a frame of reference, going across the page is X and up and down of the page is Y. Because in general physics or in engineering physics, we're only going to talk about 2 dimensions. Yeah, we can do 3 dimensions, and we even have some 3-dimensional problems in our book because I really like our author. So we got some 3-dimensional problems, but right now we're going to just kind of look at 1 dimension. And we can change that frame of reference. So my 1 dimension could be up and down a ramp, and my dimension is looking along the ramp. Or I'm looking at my X direction along the floor, or I'm looking at something up and down. So we're going to actually look at that. So we already talked about it, right? We said displacement is a state function. We only care about where I start and where I finish. So we're going to define displacement as a change in position. And we're going to use that delta for a change, okay? And as you guys start seeing it into calculus, that delta is going to ultimately become a derivative. All right. And that's because we're going to get incrementally smaller and smaller and smaller changes. And we can look at that down the road. But right now, we're just going to talk about that change in position. It's very easy to start looking at this concept of velocity and acceleration in terms of that change that we have. So I'm going to give ourselves a number line here. So we are going to look at the motion of a car, and we're going to look at it how it travels down the road, all right? We're going to look at how it travels down the road. And we're going to start with our caught rod there at a position, initial position of X sub I. We use a lot of subscripts in physics because it's going to help us keep track of what it is we're talking about. So you can use I or a little O to help us with that. And you might see that little O. Let's see if I can get that to try on here. You might see that little O on my piece. Didn't quite work, but now I can have a final position. So we've had the car move in a final position. So I'm looking at my initial plus my final position. We are sitting at 14 kilometers being our final position, and our initial position was at 0. So we have that we moved 14 kilometers. Remember, in physics, numbers have units. And keeping those units are going to help you keep through and keep things consistent. So numbers have units. So I've got a change in position. I've got a final position or an initial position. So we can look at displacement with respect to time. And now we're going to look at a new starting point. We're going to start at 1 kilometer, and that's at time is equal to 0, right? That's at time is equal to 0. And we can see that at time 120 seconds, we've now at 6 kilometers. And we look at time at 240 seconds, and we're now at 11 kilometers. And we can do time at 360 seconds, and we're at 16 kilometers. I think you can start to see that we're going to get a concept of a change in position with respect to time, kilometers per second in this case. You are familiar with that. If I travel miles per hour, we know what that is, right? We know that that can relate back to how fast we're going, and that can be related back to a speed or a velocity. And we're going to use speed and velocity, unfortunately, interchangeable, but they're not the same thing. Remember, velocity is a vector. Speed is what you read off your speedometer in your car, and it's an instantaneous value. Or we can talk about an average speed on a trip, which is going to be related to a total distance traveled with respect to time. So we have a couple of different things there, but we can do this, and we actually are going to correlate this motion into a graph. All right, we're going to correlate this motion into a graph. We know what our change in displacement is. In this case, we ended up at 16 kilometers, and we started at 1 kilometer, so we had a change of 15 kilometers. But we can plot a position versus time graph. We can look at that position. We can describe our motion using a graph. And that's really, really important. And when you guys do your video analysis of one-dimensional motion, and when you do your video analysis of two-dimensional motion, looking at that motion on a graph is very, very important. Because a graph is going to tell me something. I'm going to get information off of that graph, and we're going to see that here shortly. The slope of this line, if I draw a best fit line through that graph, that slope of that line is going to give me an average velocity. So we're going to bring back the mathematics, and we're going to show that the mathematics and the physics are tied together. So I've been talking about the fact that we have a vector. It is critical that you understand that a vector has magnitude and direction. The scalar quantity for that vector, we talk about scalars and vectors. Vectors have magnitude and direction. The scalar quantity of that vector is only its magnitude. So I'm traveling down the car and down the road, and I'm looking at my speedometer, right? And I can read what my speed is off of my speedometer. But that's just a value. That's just telling me how fast I'm going. It's not giving me my vector because I don't know whether I'm traveling north, south, east, or west. I have to have both of those components in order to understand what a vector is. And we're going to see that in two dimensions because the motion is really, really cool in that I can move independently in the X direction and in the Y direction. All right? Think about shooting a basketball. Think about traveling on a train. Think about, I can have different kinds of motion. I can be tossing a ball up and down in the air on a train, and we're both moving down the rails, but the ball's going up and it's moving and it's following me, and it's going to act just like I'm sitting there in a one-dimensional position. So vectors are very important. So displacement is the change in position, where I start and where I finish. Displacement is not the same thing as distance. So let's talk about that tossing of the ball. All right, I toss the ball up and I catch it. Its displacement is 0. The ball is right where I had it in my hand, right where I started. Now the distance traveled is something different. It went up and it came back down. And we can describe that tossing of the ball as a one-dimensional motion because it goes straight up and it goes straight down. And of course, in my picture, I show with a little bit of a gap to make it make a little bit more sense. But we can actually look at it. So my displacement's out there. So my ball, I throw it straight up and catch it, same point. The distance is twice the height. The distance traveled is twice the height. The displacement is 0. So we have that displacement 0. So the graph tells us, then when I look at a position versus time graph, it tells us that the car is moving. It just doesn't tell us what direction it is. We can get the magnitude of the vector, but I have to have more information in order to tell you where that car is moving. So I have to do it. So speed, we can look at speed, and we've been talking about speed. Speed is a change in distance with respect to time. Now, a lot of times, displacement and distance are going to be the same value. But think about swimming in a pool. If I swim to the other side and back, my displacement's 0, but the speed at which I swam is going to take into account the total distance that I traveled. So speed is going to be there. But now let's look at that equation real quick. All right, we want to look at that equation real quick. And remember, this distance final and distance initial, if I'm traveling in one dimension, this looks like displacement. But if I'm talking about and I'm reading my word problem, I have to be very, very careful of the language that I'm using. Because that language is going to tell me whether I'm worried about total distance traveled or displacement. And speed's related back to that total distance. But I want you to look at that because we've seen that change on my graph. We see that change in position. That's my change in y, right? And then on the bottom, we see time. That's my change in x. And we know that the slope is the rise over the run, or the change in y over the change in x. And we can see that speed, in this case, is going to be the slope of that best fit line. It's going to be the slope of that best fit line. So we can plug in our numbers here, and we can see that we're traveling, in this case, at 42 kilometer or 42 meters per second, or 0.42 kilometers per second. Now remember, we got to say that, does this make sense? Now we started out with a hot rod, all right? So this might make sense. And one of those numbers that I want to kind of have in your head for that rule of thumb for estimations and being able to check your work. That's why we want to have a good idea about estimations, is so we can check our work. This is a hot rod, because 27 meters per second is roughly 60 miles per hour. We don't typically think about how we travel in meters per second. We're typically going, well, is how many miles per hour, right? So we got a mile per hour kind of gauge in our head. We don't necessarily have a meters per second gauge in our head. So we want to look at that. So we've got that part in there. So we want to keep it. So the average speed is referred to as a scalar quantity. All right? It's a scalar quantity because there is no direction. Now we can also make it a vector quantity. So average speed totally ignores the variations in the object's actual motion during the trip. Okay? We don't, if we're doing displacements, if we look at that average, this average velocity in terms of a scalar quantity here, we don't care how many times I go back and forth. We're just looking at that final versus that initial. The path length and the total time are as important. And the distance depends only on for velocity, we're only going to be there dealing with our 2 points. And you can look at an S as displacement, and you can do it mathematically if you know your starting point in the X and the starting point in the Y. We don't necessarily have to travel in the X direction and the Y direction. And the path length will depend on the actual route taken. So you've got to be very, very careful as to how you interpret those particular concepts: displacement, total distance, and your actual change in distance. All right. So it takes objects a time to undergo a displacement. Well, we could do it instantaneously, but we don't have a teleporter yet. All right. So we can look at an average velocity. Average velocity looks at our final spot, looks at our initial spot divided by the time. We're looking at a change in displacement with respect to time. That change in displacement. Velocity can be positive or negative because I have a direction. Okay? We know if I'm traveling east, we know if I'm traveling west, but if I'm going up and down that number line, I can have a positive or a negative. That positive or negative tells me, am I going to the right or am I going to the left? That negative value has physical meaning. It's telling me that direction. Average speed is not the same as average velocity. Remember, average speed is a scalar quantity. Velocity is a vector quantity. So it's going to have direction. Now, if we say where we're headed with this, that change in position versus that change in time, we can also say that's the first derivative of the x with respect to time, and you'll see that here shortly. But this is where that change comes into play. And this is where that first is. So a lot of you, some of you've had calculus, some of you are getting ready to go into calculus, and calculus 1 is in there. And so here comes the fun part. We're going to actually talk about stuff in physics even before you get to in calculus. So I'm going to actually teach you the calculus that you need, and where we're going to actually tie it to make physical sense. That derivative is a real short change, and we're going to add up those short changes when we do an integration. But we're going to get there. But the other thing about this is we can talk about an instantaneous value, and that's a limit. And most of you are going to start, when you first crack into calculus, you're going to start with those limits, and this is where the physical meaning of those limits come from. So we get those average velocity. Velocity has direction, average speed does not. We can look at both cars in this case have the same start and stop. Okay? Both cars have the same start and stop, but one is going to have, they're going to have the same potential average distance, but one of them may have a greater average speed because it had a bigger distance traveled. So you have to be conscious of the fact that displacement and total distance traveled are different. So we can go back to that position versus time graph. Velocity can be determined from a position versus time graph, or our average velocity can. We still have to have some more information to give us direction. The average velocity equals the slope, and the object is moving with a constant velocity will have a straight line. I can still do this and have a curve, and that's where our instantaneous velocity comes in. And when we start to see acceleration, if I'm traveling at a constant acceleration, this is going to look like a parabola. So right now, all we've done is a constant velocity because this is a straight line. That straight line on this graph is going to tell you something. That straight line is going to tell you something. So the general equation for the slope of a line is the change in the vertical axis divided by the change in the horizontal axis. And the slope is going to carry units. So if I have a position versus time graph, it's going to be in meters per second. I'm going to have that in meters per second, and the slope carries units. So that, going back to that instantaneous velocity. That instantaneous velocity is the limit as our time gets very, 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 very small. Okay, as our time gets very small, we're going to get that instantaneous velocity. And it occurs at what's happening at the time. Or, if we do it mathematically, the slope at the tangent to the position on position versus time graph. So you may have to dust off your algebra book just a little bit to look at it. And we have that instantaneous speed is the magnitude of the instantaneous velocity. So what I want you to kind of do is think through this. Do your video notes, all right? Do your video notes. And I want you to kind of look at this information through velocity in your book. I want you to use your book. Your book is a really, really valuable resource there. And how the book explains it versus how I explain it may be slightly different, and one may make more sense than the other. They also use a little different examples, and some examples are going to hit you better than others. So I really want you to look at that. So hopefully this gets you into the velocity. We can start talking about those things, and when we come together, we can have a discussion.